Hello students, in this session we will see what is the distributed parameter models and what is the lumped parameter model. So the lumped parameter model uh, can be defined like if a given property or the characteristic of the model it is assumed to be concentrated into a single element, like in lung mechanics model which we have developed previously. The total resistance of central airways is lumped into a single quantity Rc. However, in reality, the central airways are comprised of the trachea and few branching generations of airways. So each of which has very different fluid mechanical resistances. Similarly, a single constant Cl is assumed to represent the compliance of the lung, even though the elasticity of lung tissue varies from region to region. Uh, in lump parameter models, the characteristic of particular element has been assumed to be concentrated at a single point. However, in practical situations, these are not concentrated at a single point. These are distributed throughout the dimension. So hence comes the distributed parameter models. So in order to provide more realistic characterization of spatial distribution of system properties, it is often useful to develop a distributed parameter model. This type of model generally takes the form of one or more partial differential equations with time or some other measures of the space, maybe the length, maybe the volume, as independent variables. So here we can see this distributed parameter model. So a distributed parameter model can be viewed as a network of many small lumped parameter submodels. To illustrate this relationship, the governing differential equation of a distributed parameter model of the passive cable characteristics of an unmyelined nerve fiber should be derived. So here uh, the distributed parameter model can be considered as small submodels of lumped parameter models. So here the nerve fiber is modeled as a network having serially connected multiple subunits. Each subunit consists of three elements. One is the axial resistance of 1 meter nerve tissue per centimeter square, that is represented at Rx. The resistance of 1 meter square nerve membrane is represented as Rm. The capacitance of 1 centimeter square nerve membrane is represented as Cm. It is assumed that the extracellular medium bathing the nerve fiber represents the electrical ground in this model. Target is to establish the relation between the current passing through to the voltage found at any point of this cable. So basically, the nerve fiber takes the form of a long cylindrical conductor of radius A. The analysis has been conducted for a small length, that is delta x, that contains one subunit. So basically, the model will be developed for this subunit. And it is assumed that the intracellular voltage increases by delta V and the axial current to increase by delta I over this small segment of cable. So the assumption of increases instead of decreases in voltage and current merely establish a sign convention. So in reality, the voltage along the nerve fiber drops as current flows out of the nerve fiber through a leaky membrane. If the adapted sign convention results will show the change in voltage or with length with negative sign. So the voltage increase delta V occurring over an axial distance delta x is related to the axial current by this particular equation. Further, if we transfer this particular term in the denominator, we will get this particular equation. So the membrane current delta I is related to the intracellular voltage V by this particular equation. And similarly, this particular equation can be converted into this form if we send this particular element in the denominator. So the right hand side of equation bears a negative sign, since the increase in voltage should be associated with the current flowing in the direction opposite to the assumed in the figure. Differentiating equation 1 and equation B with respect to x and substituting the value of delta I and delta x in equation B, we will get this particular equation. So this equation is known as the one-dimensional cable equation and describes intracellular voltage along the nerve fiber as a continuous function of length and time. So like this, we have developed the distributed parameter model for a nerve fiber.